Yeah. I think the next talk has at least my personal prize for the best talk title for the so yeah, down with the state, I guess.
Yeah, something like this. Okay, so hello everyone, and thank you for being here. I'll be talking a bit about, this is actually not really talking about an achievement, but more about a problem that we've bumped into repeatedly in Nantes. And yes, it feels like a Pierre-Marie Pedro title. He might have been the one inviting me to submit to it, so there is no coincidence. But so yes, the problem I want to talk about is how to handle eta-conversion in Coq, in particular in the settings of the MetaCoq project. So let me set up the scene first. So as probably most of you know, Coq has eta-conversion because it's the 21st century. Everybody should have eta-conversion. So if you write this in Coq, and you can just prove that equality by reflexivity because f is the same as its extension. And we have it for function, and Coq also has it for primitive records or strong sums or negative sums, name them the way you want. And I won't talk about them here today. I'll talk only about functions, but the problem is probably pretty similar. So most of the things that I say here should probably apply. And what happens under the hood is that you have an n-typed conversion test. So it's quite important, and it's very an important part of the design of Coq, that no types are maintained during conversion testing. We maintain the invariants, that terms that we consider should be well-typed, but those types are actually not maintained by the algorithm. And how the algorithm works is that it reduces the terms to weak head normal form. And whenever it sees that you're trying to compare a neutral against an abstraction, as is the case here, you have on one hand, you have the neutral f, and on the other side, you have that abstraction here, then you eta expand the neutral using the information coming from the abstraction. So you never use the type information to do your eta expansion. What you use instead is the information of the thing you're compared against. And actually, this works quite well. And the implementation is not the troublesome part. So I know it's supposed to be a workshop about implementation, but the issue I want to talk about is not an implementation issue. This algorithm seems to work very fine. The problem is how to specify it. And the place where we want to specify it is inside MetaCoq. So if you've heard Mathieu Souzo's talk, you already know a bit about this. The general aim, let's say, is to mechanize the meta theory of Coq inside of Coq, and to use that meta theory to implement and prove correct and complete a type check. So really have a nice kernel that we've proven correct all the way. And the way this works is we have actually two notions of conversion lying around. We have the what we've called declarative conversion. This is maybe the one you're used to. You have all your transitivity and congruence closure rules, and of course the base cases like here beta reduction. And this is the thing you see in the high level specification of the system. And then to prove any properties about this, we actually have to introduce another notion of conversion, which is much more structured, that we've called algorithmic conversion. And here two terms are dubbed convertible when they're reduced to things that are basically the same up to names and a few universe things, but really alpha, let's say alpha equal here. And this is much more structured. You, in particular, you don't have this crazy transitivity rule. You have to invent this middle term somewhere. And so you have some good properties of this algorithmic conversion that you don't have on the declarative conversion. And the general plan of proof for the meta theory is first you have quite a bit of sweat on those conversions. So you need to prove confluence of the reduction relation that we use. You also have to prove a simulation property, saying that if you have two equal terms and one of them reduces and also the other reduces something that is, again, alpha equal. And once you've done this, you can prove actually that the algorithmic relation is transitive. And from this, it's easy to show that the algorithmic and the declarative conversion are equivalent. And this is done on all terms. Here, we haven't talked about typing at all. And this is quite important. And once you've proven this, you have two notions of conversion that are equivalent. And this is nice because now you can prove using the algorithmic conversion that naturally has the injectivity of subconstructors property, and the declarative one that is transitive. You can have all these properties at once, and then you can use that to prove subject reduction. And this is the main theoretical property that we want. And from that, you can prove that the conversion tests and the type checkers meet their specification. So that's the plan. First, sweat on the untyped in the untyped setting using reduction. Once you've done that, the rest of the meta theory follows. I mean, it's still quite long to get there, but the maybe most crucial points are up here. So that's the plan. And now we want to extend that plan with eta, because until now, the reduction I've told you about, it has beta reduction and iota reductions and all kinds of other things like definitions and whatnot, but it has no form of extensionality. And of course, we have it in the kernel, so we want to add that to our specification. And so there are basically 3 ways to do so. The first one is to extend reduction with eta, and to orient eta as an expansion. So whenever you have a function, you can reduce it to its eta expanded form. And everybody knows that it's the way to go. There's this paper on the virtues of eta expansion that goes quite a while back now, and all kind of categorical reasons or whatnot to do this. This is what is done in normalization by evaluation. This is what everybody does. But the problem is that, remember, we don't have any types lying around. And especially the reduction here that we want to have is one that does not talk about types. And of course, if you're in an untyped setting, suddenly this rule is much more scary, because we need to invent somehow that annotation on the binder. And also you want to know when you launch that rule, and it might endanger normalization or create loops with beta and this kind of things. So if you don't have the kind of control that types provide you with, expansion gets quite hairy. Another possibility is to still have reduction, but now put it the other way around. Now you have really eta reduction. You cancel the abstraction if a variable is not free. And this goes a bit further in the setting we're in, but it still has some weird implications. In particular, if you look at that term, so okay, I'm talking here about conversion, but actually Coq has something that's a bit stronger, namely what we call cumulativity, that also allows you to go up in universe levels. And this makes this kind of term typable, where you have a variable at level 0, and you feed it the identity of level 1, and then the x kind of gets bumped up in levels. But the problem is that this thing, it reduces by beta here, and you can also eta reduce it in the other way. And now you see that you have 2 terms that are reduct of the same term that do not have the same annotation. So in a way, they have the same intentional meaning, but the annotation is not the same, and so you've lost confluence. And also, which is even more subtle, this also breaks subject reduction. And here is, so if you look at the term here, it has this type, it abstracts on a variable of type 0 and returns something of type 1. Now the reduct here, it abstracts on a variable of at level 1, so it's of type 1 to type 1. And the issue is that in your usual notion of subtyping, this is a subtype of that one type, and so the abstraction also has that type. But in Coq, cumulativity does not have this covariance on the domain of product types, mainly because the models, the set models that it's used to model cumulativity does not have this. It's not that easy to model this contravariance, and so this means in the end that the reduction here does also break subject reduction. And of course, this is an important property that we don't want to break. So it's another issue here. But there's actually a third solution, which is to not to take inspiration from the kernel and from the implementation, and to not incorporate eta inside the reduction, but to instead put it inside this alpha equality. And do actually what the kernel does. If you have a term against an abstraction, then you can just somehow eta expand it and then compare the eta expanded form with the body of the abstraction, of course, on the other side. And this works actually quite nicely for a while. But again, you hit a wall, and this time the wall is the simulation property. So if you have this nice iota redux, you match on true, and of course this reduces to 0. But now you can somehow eta expand true, and you get something that does not reduce anymore. So here the issue is seemingly only on ill-type terms. But remember that we want our properties to hold on all terms, because we want the properties of reduction to not be linked to typing. And the reason for this is that if we had this only on well-typed terms, then we could prove only transitivity if we know that reduction preserves typing. That is, if we have subject reduction, but subject reduction is proven using injectivity of type constructors, which is proven using transitivity of the algorithm duration. So we have a cycle here. And so at least we cannot keep the same plan if we want to implement eta this way. So that's kind of sad. And that's the thing we've bumped into repeatedly when trying to incorporate this in MetaCoq. I mean, we don't really have a completely good plan yet, although we have a few ideas. The first one is, so reduction has issues, but maybe we can kind of go around these issues. We had issues with annotations, but quite a few people go well with unannotated lambdas. I mean, Agda doesn't have annotations anywhere, and it works well. And there are already papers actually on pure type system without annotation and showing that conversion with and without annotation should be equivalent. So maybe we can try something like this. And for the subject reduction issue, then we could either move to contravariant products, maybe find the right model for cumulativity or something, or actually have a notion of reduction that doesn't have subject reduction, because the kernel actually never uses eta reduction. So maybe it's not that terrible if we have a reduction that is not completely, that doesn't really have subject reduction. Maybe there's something to do here, but at least it requires quite some work, and maybe also a change, a quite heavy change in the specification of Coq. And for equality, well, maybe if we can find a way to cut the loop, then we'd be happy. But this would probably make things much less modular than they are now, and the file is already a few thousands of line long. So having everything all at once might not be a good idea. And the other solution, which is maybe much more ambitious, but also might be more interesting, is to completely abandon our current plan and move to typed conversion or typed equality. And if you look at the summary of changes of Coq, when eta-conversion was introduced, actually there's this small phrase saying that the addition of eta-conversion is justified by the confidence that the formulation of CIC based on type equality is applicable to the concrete implementation. So somehow the people that implemented eta, and I guess that's Hugo Herbelin, thought about type equality as the specification they had in their head. So maybe that's a way to a good way out. But here we have one issue is that we've already quite a lot of code and quite a large development that we just would have to throw away, but maybe that's life. And the other issue that's maybe more profound here is that all the proofs I know about such systems with typed equality, they require a very strong logical power, usually in the form of induction recursion. And actually, one of the neat things about MetaCoq is that the whole meta theory I've told you about, it's done with the logical power of Coq. And only at the end, we introduce a normalization axiom that we use to derive the type checker. But the whole meta theory is done in Coq with the logical power of Coq. And so I'm not sure we can actually do the same kind of development in Coq if we had a notion of type equality. And moreover, I have the feeling that this kind of induction recursion proof, they are very monolithic and very, very large. And I think for a language the size of the actual Coq language with like huge AST and things like that, I'm not sure it's actually feasible to do a proof with using this tool. So I don't know if this is actually a good way out or not, but yeah. That's it for me. Thank you very much. And I'd be very happy to have any feedback you have or ideas you'd have on this.
Okay. Thank you very much for the talk. Let's see if there's any questions yet. No online questions yet. How about offline?
Hello, yeah. Just a quick question about that reduction at the beginning with the poor interaction with cumulativity. I was just wondering, in that context, could we, assuming we were working in some kind of type system that did have the contravariance described for pi types,
yeah,
could we view eta-conversion as a cast to a pi subtype, which would be a pi with the parameter type as the supertype, and so then kind of subsume that in a rule that a null cast gets optimized away? So eta optimizes to a cast, and then null casts. Eta reduces to a cast, and then null casts reduce themselves to nothing. Could we do that in a typed reduction system?
Interesting. The feeling I have indeed is that somehow I agree with you that somehow eta in that context feels like a form of optimization, where you actually like you throw away the bad binder you had and you reduce to the core function that might change the binder. But I'm not sure how what you say would work. But that might be something to consider.
Because you already need a framework for casts, right? So you could reduce the eta framework to just the cast framework, because it seems that
so the point here though is that cumulativity is completely implicit. So we don't have casts anywhere, and I don't think we would want to change that. That's also it's also maybe a good point of Coq compared, I think, to Agda, for instance. We have to actually tag the places where you use cumulativity by hand, if I'm not mistaken. That's
Agda's universes are not cumulative though, so I don't think it's a exact comparison there.
Yeah, it's not exactly the same. That's definitely a good thing that we don't have to sprinkle those casts all over the place. And I think it would be nice to keep that, but yeah, I don't really know.
I do see another question online, but just I'd like to preserve some of the break. We have to start up again in 10 minutes here, because we're going to actually get kicked out of this room right at 5:30. So we need to make sure to stay on time for the next session.
So okay.
So thanks very much.
Thank you. And I guess if people want to discuss it much, I'll lurk in the lounge. So feel free to come and discuss, I guess.
Great. Thanks. So we'll resume here in 10 minutes.